our second example of the demonstration of the method of contour integration solution of the differential equations with linear coefficients would be the following slightly more complicated differential equation. Our goal would be to find the bounded at x tending to plus minus infinity solution and the additional condition would be that the solution should be normalized at the origin by this condition. Right. So let's follow our standard scheme. First, build P and Q polynomials. The P polynomial is simply 2i. The Q polynomial is t squared plus 1. Now we compute the standard integral. Well, the typical mistake that student makes is that he usually uses the standard antiderivative, which is arctangent here. Try to avoid it. Instead, use log function whenever possible. So here, for example, let's expand the integral into simple fractions. It's very easy to do. Here, so you may have guessed that the numbers here was specially tuned to make things simpler, right? And finally, we get the log function. Now we are ready to write down the constituent function which define our solution, namely the function which is simply e to xt times t minus I divided by t plus I. And z function, which is almost v function but divided by q polynomial and without this exponential term. So it's t minus I divided by t plus I multiplied by t plus I by t in the denominator by t minus I. So what we get is 1 over t plus I squared. And finally, our solution, u of x, is some contour integral of e to xt t plus I squared dt. And now the key part, the choice of the contour. So let's draw a complex plane of t variable and point corresponding singularities or special points of our v function. So v function has the pole at point minus I and the root, first order root at point I. The integrand only has the pole, the second order pole at a point t equals to minus I. So one of the possible choices of the contour is clear. It's simply the closed loop around the pole. And immediately we find the exact solution. Here we go. So let's call this contour gamma 1. And u1 of x is simply equal to the residue of the integrand at point t equals negative I. the residue is trivial to compute. And we arrive at the simple result. So perform one differentiation, which gives us prefactor x, and finally we obtain 2 pi I x times e to minus I x. Oh, quite nice solution, but the problem is that it's unbounded at x tending to plus or minus infinity, because the modulus of u1 of x behaves as the modulus of x. And even worse, at x equal to 0, it can't be normalized. It's equal to 0. So this solution doesn't satisfy us. So let's study another solution, which is defined by the second contour, which is not drawn yet. So let's draw it. Well, first of all, we recall that our v function vanishes at point t equals I. Unfortunately, it's not possible to draw a closed contour for the second solution. So we have to improvise a little bit. And when we look at our v function, we realize that as soon as the real part of xt tends to minus infinity, if t goes to infinity in the complex plane, then that would be the possible end of our contour. So because the beginning would be at point t equals I. And we just need to analyze how this thing, this real part, behaves at different arguments of x and t complex numbers. Well, suppose x is an arbitrary complex number, and we reproduce it as we decompose it into the exponential form. So it's modulus of x times e to I alpha, where alpha is the argument of x. Now t, accordingly, is represented in the following manner, in the same manner. And when we take the real part of this product and require that the real part tends to minus infinity, it's equivalent to the condition that the cosine, to which the real part is proportional to, the cosine of alpha plus phi, that's the sum of these two arguments, is negative. And in this case, if this condition holds, then we achieve the vanishing of our v function. So let's see what it means for our phi angle. So phi, the argument of our t variable, should belong. So let's sketch that kind of region in our complex plane. Well, first of all, suppose alpha is some small angle. So then the region from pi by 2 minus alpha to 3 pi by 2 minus alpha looks as follows. So it's subtended by the following line. And here are the possible direction of our contour. So the contour starts at point I, because this is the point where the function vanishes, and goes into any of the possible directions, like probably here, here. And by the way, I forgot to mention that, of course, this inclination angle is simply our alpha here. Right. So let's actually let me show you some particular characteristic direction. For example, if alpha equals 0, then x is purely real and positive. In this case, here is the vicinity of our point I. And the corresponding region is just the following semicircle. So phi belongs to the segment from pi by 2 to 3 pi by 2, precisely this. And here are the possible directions of our contour. Now, suppose, so it's alpha equals 0. Suppose alpha equals pi by 2. Then the whole picture rotates by pi by 2. And what we get is, so this is our I point. and what we get is this region. And the contour starts at point I and goes in any of these allowed directions. So we can check. It should be from pi by 2 minus pi by 2, from 0 to 2 pi, precisely this region. And that corresponds to the case when x is purely imaginary, and so it's imaginary is positive. Next would be the region, for example, alpha equals pi. Important for us region because we need to estimate our solution at x tending to minus infinity, and alpha equals pi correspond precisely to this case. And the allowed segment for phi is from minus pi by 2 to pi by 2. So the whole picture rotated from this position to this position precisely by pi. Okay, now let's look at the structure of our solution. This integral can't be taken exactly, so our best bet is to find its asymptotics at large values of x and normalize the whole solution by this normalization condition. So keeping this in mind that we need to perform the asymptotic analysis in the end, let's figure out what would be the steepest descent direction for the integrand, because it contains this exponential, and for large x, the integral is taken with this steepest descent direction technique. So we have this condition for the allowed regions of our phi angle, allowed values for our phi angle. However, the steepest descent direction is defined by the least possible values of the real part of the exponent, namely when cosine of alpha plus phi is the least possible number. For cosine it's negative 1. So steepest descent direction, cosine of alpha plus phi is negative 1. So phi is equal to pi minus alpha. So look at the region of the segment to which phi should belong. It's from pi by 2 minus alpha to 3 pi by 2 minus alpha. And here is the steepest descent direction. It's pi minus alpha. It's a median. It's a median. It's this direction. So we make all the things significantly simpler if from the very start we direct our contour in the steepest descent direction. For alpha equals 0, it's this direction. For alpha equals pi by 2, it's this direction. It's pi by 2. And for alpha equals to pi, which is when x tending to minus infinity, it's this direction. Again, pi minus pi, 0. Right. And finally, let's analyze the behavior of our solution. Well, first of all, let's figure out what would be the correct normalization factor in front of our integral. I didn't write it here at the very start, but now we need to restore it and fix it. So x equals 0, then u of x is turned into quite a simple integral. Suppose, for simplicity, x is positive. We'll see that the normalization doesn't depend on the value of x. Then the integral is a at x equals to 0 from point I to, in this particular case for positive x, from I to infinity, minus infinity, dt over t plus I squared. It's an elementary integral with very simple antiderivative, which is minus 1 over t plus I. And now we understand why the value of our integration, our normalization constant doesn't depend on the value of x, because this function at plus or minus infinity or infinitely distant point, I mean 1 over t plus I, behaves identically. It's just 0. So the integral is simply a over 2I. And hence, the constant a is simply 2i. So we fixed the normalization constant for our solution. And our next and final step is to check if the first condition is satisfied, namely that u of x is bounded at large positive and negative values of x.